So thank you for the introduction, and so I'm going to tell you about a practical application where we're using artificial intelligence in the field of pathology in a medical field. And so as mentioned, we are a spin-off company from this campus, from the Institute for Molecular Medicine. And our product is called Web Microscope. It's a cloud-based intelligent platform for helping pathologists and researchers in their work. So in this talk today, I will first describe you the challenges in the pathology field today, and then tell you more about how we're using deep learning artificial intelligence to help our customers in their work. So if we look at the challenges in the field of pathology today, cancer gives us a good example. Due to aging population, there's more and more new patients each year, and this is constantly increasing the number of samples to be analyzed. However, the number of pathologists is not following this trend, and in fact, many countries and areas suffer from the lack of pathologists. For example, in China, there's 20,000 pathologists, and the number should be 100,000 to be on an adequate level for the population. Microscopy plays an important role in cancer diagnostics and in all anatomical pathology diagnostics. However, it's a subjective manual analysis based on visual methods in many places today. And this causes, of course, some risk to the variance in the interpretation, which may vary from pathologist to another or from time to another. So there's both a challenge to increase the efficiency and the consistency of the analysis. And the first move to improve the situation is to digitalize the samples. And this is an increasing trend in this field today. Digital images are of course easier to archive, retrieve from archives, send to remote consultation. But the most significant improvement and benefit is the ability to use machine vision and deep learning artificial intelligence to help the experts in the analysis. There are some challenges as well, and the first one is that these images of tissue and cell samples, these are huge files. And the microscope scanners doing the digitalization, they all have their own locked image file formats, which makes them difficult to share with collaborators having a different vendor of an instrument. The image analysis software and tools available on the market are expensive on-premise installations, and they're based on conventional so-called first-generation machine vision methods, which are in many ways limited. So we've developed our web microscope to address these challenges, and we are providing fast and easy access to this image analysis tool on a cloud platform. And this is how the workflow goes. So our customers have their samples on slides. They do the digitalization with any microscope scanner they have. And after that, the images are uploaded to the web microscope. And once the images are there, they can be viewed with an internet connection with any browser, any tool, anywhere our customers are. And we sell this software as a service, so our customers have their dedicated password-protected accounts to their own image collections on a web microscope, where they can run the image analysis tools, the algorithms that we provide for them. And this way, it's also, they don't need to invest in local capacity for GPUs or for image servers. So this is also as a platform that they can purchase from us. And this white part of the cloud here is something what we've sold as a company for 3 years now, and we've just launched the next version of the software with artificial intelligence on top of the platform. And artificial intelligence and deep learning, it's of course utilized in various applications, and you've all heard about facial and speech recognition apps or companies teaching cars to drive themselves. So we're teaching these deep artificial neural networks on and training them how to detect certain features in tissue samples like cancer cells. And this is actually, so in this approach, we're teaching these neural networks for each specific application separately. And these applications can be like laborious quantification tasks from the samples, or segmentation of tissue based on morphology, or it can be detection of some rare targets from these enormous images, which is helping the experts to identify the targets of interest. This is one application example. This is a tedious quantification task routinely performed in breast cancer diagnostics and research. It's about quantifying the Ki-67 biomarker from the epithelium part of the tissue. And when starting to develop these new image analysis algorithms, we start by selecting a set of images for training. And in this part, it's very important to have a variance of all the samples to be studied later on in the training set. So if we know that the staining intensity will vary later on, it's good to have those examples in the training set. And in this application, we sort of have a benefit of having a lot of image data already in one single sample. And these are so huge images that we cannot annotate them all. So we take small snapshots from different parts of these images and thoroughly annotate and teach the neural networks to learn different targets. And this is the most important step in this process, I would say. And this is an iterative process, so we teach as long as we've reached the desired sensitivity and specificity level in the detection. And in this particular application, we first detected and segmented the tissue epithelium from the stroma part, and then quantified the biomarker inside the epithelium. And in web microscope, we show the results of the analysis on top of the original image as a pyramid structure. So one can really zoom into a cellular level to see visually the results. They're of course also displayed as numbers, which can be exported to Excel. So this kind of context-intelligent image analysis enables to automate the whole process. And this is something unique to this market. So we can help our customers to remove manual steps from their workflow or remove extra staining step in their work and thus save time. And if you compare to manual visual analysis, this kind of automation is always the same, the analysis, so we can give accurate and reproducible results and support pathologists in their work. This is another example. This is again a quantification task, but this is from fat tissue, and here we are quantifying the percentage of fat, so these white small droplets of fat inside the liver cells. And this particular sample is from a large set of research samples, hundreds of them. And the task for the pathologist is really to quantify the number of fat. And you can imagine that visually manual with the basic conventional microscope, it just needs to be an estimate. You cannot calculate exactly. And you need to be very thorough in your own standards. How do you analyze various samples when you need to do them during several weeks or so? And so we've automate this whole process and train the network to learn how does a droplet look like and how does it differ from the vein part, which is a blood vessel holes inside the tissue and so on. And also the background is white, so this was a sort of a challenging application. But with this algorithm, which is now complete, we can get consistent accuracy and reproducibility over the larger number of samples in this application. And there's really an endless number of various applications available for us to do algorithms for. And this is just a list of algorithms we've created and examples of those. And many of them relate to cancer, but there's also ones for gastrointestinal diseases and algorithms for studying neurodegenerative drugs. For example, the picture here in the bottom, it's a very complex image where we've identifying and calculating the number of nerve cell bodies. And our aim as a company now is to create a list of these algorithms and provide them on our web microscope platform for the users to be utilized. And the benefits compared to manual visual analysis are quite clear, but if we compare this technology to conventional sort of first generation machine vision methods, We can enable automation of really complex image analysis tasks with deep learning. This saves time. The teaching of new algorithm takes a few days or weeks compared to months that it used to take before. It's also possible to retrain the network if there's some variance in the sample sets later on. And we have an affordable business model which supports also small projects or single users to start using this software. One can say that the future of pathology is really digital. We can see a lot of benefits in using artificial intelligence and deep learning in this field. We are now in a status where we can support the decision making with quantitative data from the samples, so we can give numerical data, we can segment tissues, or we can identify certain areas to help the experts. But I'm sure that we will soon be able to suggest a prognosis based on the morphology of the tissue, and we will be able to suggest a treatment for the patient when we dig into the big data of patients with similar symptoms, similar genetic profiles, similar morphological data. And all this is clearly for the benefit of the patient, as it provides faster and more accurate diagnosis and cure. And to the end, I'd like to highlight our experienced team, which without this we wouldn't have all these tools available. And I would say that we are really a mix of expertise. So we have medical doctors in the team, we have entrepreneurs, we have software developers, machine vision gurus, and commercial expertise in the team. So, and besides the core team here, we have 8 people working in the software development and algorithm development. And we're now in a status where we've just launched the next generation version of our software and are really putting a lot of effort to ramping up the business globally as fast as possible. We are currently recruiting and looking for new investors, so if you're interested to learn more, please contact us. Thank you.